Okay, so we're going to look at a problem relating to net force. So the problem reads, a 6-kilogram block is being pushed on by 2 kids. Kid 1 stands to the right of the block. The force from Kid 1, F1, is 13 newtons, and he is pushing down on the block of ice at 30-degree angle with respect to the horizontal. Kid 2 stands to the left of the block of ice, and the force from him is 11 newtons, and he's pushing down on the ice at an angle of 60 degrees with respect to the horizontal. The table is also exerting a force of 74.8 newtons upward on the blocks. It says stay tuned, we'll discuss this special force later. We're going to call that the normal force for those of you who've already looked ahead on the material or using this to practice in the past. What is the net force acting on the block? All right. So we're interested in net force. We're going to do a net force analysis. And let's draw a picture of our situation. So here's our block of ice. We said we have one kid that's standing on this side and he's pushing down on the block of ice. We have another kid who's kind of pushing in the opposite direction of the block of ice. And they're standing there on some surface. So the object that we're interested in analyzing is the block of ice. So that's our object. All right, and because we're interested in the net force, we're going to do a force analysis. And that first step of a force analysis is a free body diagram. So I like to just use a dot for my object of interest being the block of ice. And then I need to think about what are the interactions that this block of ice is experiencing, and how do those interactions turn into forces on my free body diagram. So what is one interaction? Well, we know the block is exerting a force on the table, and the table is exerting a force back on the block, and that's given in the problem. So we have the force of the table, and that is between the block and the table, and the table is sort of pushing up on the block. So there's my force of the table, and that is given to equal 74.8 newtons. All right. Well, the block's interacting with the earth, so we have the force of the earth. We call that the force of gravity. That's between the block and the earth. And we know that always points down towards the center of the earth. So that points down. We know that the force of gravity is equal to mg, and our block is 6 kilograms times our 9.8. So our force of gravity is 58.8 newtons. All right, well, then we have this kid, kid 1, it says kid 1 is pushing down at the ice at an angle of 32 degrees. He's standing to the right of the block. So he's pushing down on the block like this. So he's pushing down like this, and here's my angle of 30 degrees. And they're pushing at 13 newtons. That person is pushing at 13 newtons. And the other kid is standing on the left of the block. It says he's left of the block. He's pushing down on the ice at an angle of 60 degrees with respect to the horizontal. So there's my horizontal. So he's pushing at 60 degrees with respect to the horizontal with a force of 11 newtons. So those two interactions we can also add. We have the force of kid 1, which is between the block and kid 1. And then we have the force of kid 2, which is between the block and kid 2. All right. So now let's look at the net force. Well, in order for us to look at the net force, these are vectors, so we have to add them vectorially. So we are going to have the horizontal components of the vectors, and we're going to examine the vertical components of the vectors. We're going to split up horizontal and vertical, our independent coordinate system, and then we are going to add them up for horizontal direction, add them up for vertical direction, put it all back together. All right, so let's number our forces. So we have the force of gravity, we'll call that 1, we'll call this one 2, 3, and 4. Force number 1, well, that's the force of gravity. Okay, so the horizontal component, well, he's pointing straight down. There is that one. And the vertical component, it's negative mg, which we know to be negative 58.8 newtons. All right, that negative indicates it's pointing down, remember. Okay, force number 2 is this one. That's the force of kid 2. So it has both a to the right and downward piece. So the horizontal component is the force of kid 2 times the cosine of the angle, this angle here, which is 60 degrees, negative 60, because it's relative to the x-axis. And so that is equal to 11 times the cosine of negative 60 degrees. And that is equal to 5.5 newtons. The vertical component is F2 times the sine of the angle of negative 60 degrees. So we have 11 times the sine of negative 60. And that gives us negative 9.53 newtons. That's force 2. And it's from kid 2. Force number 3 is the force of the table. There's no horizontal component. The vertical component is pointing up, and it equates to 74.8 newtons. Force number 4 is the force of kid 1. It has a horizontal component related to the angle. Now I'm going to use the other method just to give you practice on both. I know this is 30 degrees, so my horizontal component, this component, is going to be adjacent, or the cosine of 30 degrees, but it's pointing to the left, so I have to make sure I remember that negative. So minus force of 1 times the cosine of 30 degrees. So since I'm using this internal angle, I have to put that negative in explicitly. So we have minus 13 times the cosine of 30, which is negative 11.26 newtons. Similarly, vertically, I'm going to use this 30 again. I am opposite that 30, that's a sine, but I'm pointing down, so I have to make sure, since I'm using that internal angle, I put my direction in explicitly, so I have minus F1 times the sine of 30. So minus 13 times the sine of 30, and negative 6.5 newtons. All right, so I am going to sum my forces in the horizontal direction and sum my forces in the vertical direction to get the net force. So that's all these values and all of these values. All right, so let's sum them. We get 5.5 minus 11.26 is equal to the forces in the horizontal direction. So 5.5 minus 11.26, negative 5.76 newtons are the forces horizontal. Vertically, I have minus 58.8 minus 9.53 plus 74.8 minus 6.5. So minus 58.8 minus 9.53 plus 74.8 minus 6.5, and I get negative 0.03, so that's about equal to 0. And that is the force in the vertical direction. So now I have my net force acting on this block of ice in its horizontal and vertical components. I can put that back together, but I can recognize something particular about this situation. I don't have a vertical component, so therefore I have no component in the vertical direction. It's along the x-axis, and it's negative. So my force on the ice, in total, the sum, or the net, is equal to 5.76 newtons at 180 degrees. Horizontally, it's only got a force, net force horizontal, because everything else cancels in the vertical direction. All right, so recognizing the object, setting it into a free body diagram, looking at those interactions to make sure we have every force in our free body diagram, separating those forces into vertical and horizontal components, putting them back together to determine the net force. All right, good job.